Hello, welcome to another video lesson episode with me. I am Sir Von, and for today's presentation, I'll be talking about one of the critical contents that grade 9 pupils of grade 9 students of the Department of Education find difficult, or what the Department of Education classifies as a critical content in physics, and that is projectile motion. Let me now share my screen. In this presentation, I've decided to have a pretest which gives 10 items as initial questions. And at the end of the lecture, you'll be seeing the answers to the 10 item questions that I prepared. So let's begin. Item number 1 is, when a teacher throws an eraser from the front to a door 6 meters away, how do you call the parabolic path taken by the eraser? A, projectile, B, trajectory, C, range, D, height. So ideally, in answering these questions, you should have a pen and a paper with you, so you can quickly write your answers. Item number 2. When a ball is thrown by a physical education teacher, the ball follows a parabolic path. What do you call the ball in this case? A, projectile, B, trajectory, C, range, or D, height. Item number 3. A ball thrown at a certain angle is aimed to travel the farthest. At what angle with respect to the horizontal will accomplish this? A, 0, B, 20, C, 45, or D, 90. Number 4. At what angle with respect to the horizontal should a ball be thrown to travel the highest? A, 0 degrees, B, 20 degrees, C, 45 degrees, or D, 90 degrees. Number 5. Which of the following statements about projectile motion is not true if air resistance is neglected? A, the graph of V versus T for horizontal and vertical are the same. B, the acceleration of the projectile is constant throughout the flight. C, the horizontal and vertical components of motion are independent. Or letter D, the time it takes for A to ascend, or for it to ascend rather, equals the time it takes to descend to the same height. Number 6. Two vehicles fell off a cliff and follow the paths X and Y as shown in the figure below. Which statement below is true about the situation? Here's the figure. Item 1, they covered the same horizontal displacement. Item 2, they have the same vertical acceleration throughout. Or item 3, their velocity components along the horizontal are the same. Letter A, 1 only. Letter B, 2 only. Letter C, 3 only. Or letter D, 2 and 3. Item 7. A ball is thrown from a cliff and follows a path similar to the figure below. Neglecting air resistance, which of the following statements about the falling ball is correct? Number 1, the vertical acceleration of the ball increases. Number 2, the vertical component of the velocity of the ball increases. Or number 3, the horizontal component of the velocity of the ball increases. A, 1 only. B, 2 only. C, 3 only. Or letter D, 1, 2, and 3. Item 8. A soccer ball is kicked by a player during a match. Which pairs of velocity versus time graphs represent the horizontal and vertical components of the object as it reaches the maximum height? A, Look at this graph for velocity versus time. That's horizontal velocity versus time. And this is vertical velocity versus time. And letter B, look at the graph. This is again horizontal velocity. And the second graph is vertical velocity versus time. Letter C or letter D. Item number 9. After hitting a ball or baseball, the horizontal speed was measured to be 30 meters forward and its vertical speed was 35 meters per second upward. Ignoring air resistance, what is the value of the velocity 2 seconds after? Consider that the acceleration due to gravity is 10 meters per second or 10 meters per second squared. A, 30 meters per second horizontally, 35 meters per second upward. Letter B, 30 meters per second horizontally, 15 meters per second upward. Letter C, 5 meters per second horizontally, 35 meters per second upward. Or letter D, 5 meters per second horizontally, 5 meters per second upward. Item 10. A tennis ball was hit, giving it a vertical speed of 10 meters per second upwards and a horizontal speed of 25 meters per second. How far will it be able to travel horizontally? A, 15 meters, B, 25 meters, C, 30 meters, or letter D, 50 meters. That's the last item. So at the end of the pre-test, you should be able to complete answering all items. But in the event that you failed to answer the items or a particular item, you can pause and you can repeat that particular item or go back to that particular item. So now we can have the details of the topic, which is projectile motion. In understanding projectile motion, we can consider a lot of examples that we can see around us, such as what's shown by the pictures given in this slide. You notice that a person playing a basketball and the path that's taken by the basketball is similar to that of what happens when a person is welding, and the path that's taken by water here on the third picture. Now, let us consider two identical balls released at the same height, say balls A and B. Ball A is allowed to fall freely, and ball B is given a horizontal force or given a force along the horizontal, or exerted a force along the horizontal. So the big question here is, which do you think will reach the ground first? Will it be ball A or ball B? Or the balls will reach at the same time, or the balls will reach the ground at the same time? Let us now examine the strobe of the balls asked in the previous slide. So if you'd notice what happens to the two balls and the distance they travel along the vertical, they have the same positions with respect to the vertical. They're falling at an almost the same rate. So notice that the red ball is dropped and the yellow ball is fired horizontally. So notice in that particular presentation that the balls have almost the same rate of fall. Now let us consider the picture that I've shown initially, where a person, a basketball player, throws a ball to the hoop. In this particular example picture, you notice that the ball is considered to be the projectile. Now, what is a projectile? So a projectile is any object. Say it could be a ball, it could be anything that is given an initial velocity and then follows a path determined entirely by the effects of gravitational acceleration and air resistance. So when you throw a ball, it will follow a particular path. The path that's taken by that projectile is called the trajectory. So essentially, when you throw a ball, its motion is a combination of horizontal and vertical motion. Its horizontal motion has constant velocity, and its vertical motion has constant acceleration. As fundamental concepts, we note that acceleration is defined as the rate of change of velocity, or that is the change in velocity per time, where velocity describes the change in displacement per time. So when we say that the horizontal motion has constant velocity, that means that there is zero acceleration for the horizontal motion. And when you say that the vertical motion has constant acceleration, that means that there is a constant rate of change of the velocity. That rate of change of the velocity is associated with the pull of gravity, making us have for Earth the acceleration due to gravity be approximately around 10 meters per second squared, or that is, in some references, that's 9.81 meters per second squared. The direction is downward, since the acceleration of objects is downward. And in some references as well, the negative sign is included as part of the value of the constant. Here is the path taken by a projectile, and that path is called trajectory. Notice that this illustration of the path of a projectile showcases some interesting points. These arrows actually represent the vector's velocity. There. Notice that the vertical component of the velocity of the ball decreases in size up until it reaches that maximum height. That's the maximum height. And at that maximum height, the velocity component along the vertical is zero. And as the ball descends once again, notice that the vertical component of the velocity increases as shown by larger arrows. Notice, however, that the velocity component along the horizontal does not change, as illustrated by equal lengths of arrows in our figure here. The distance covered by a projectile from this initial position to a certain position is called, along the horizontal is called range. Or you can generally call it displacement along X. And displacement along Y is the change or associated with the change in the position of the object along the vertical. Notice again that the X and Y components of motion of a projectile are independent of each other. That means that the motion of the projectile along the horizontal is not affected by the motion of the projectile along the other component. In discussing projectile motion, it's also important for us to know the details of the two components. That's the X and Y component. And one of the things that we are most concerned about when discussing projectile motion is the velocity. So we can talk about velocity component along X, and in a while, we'll talk about the component of the velocity along Y. although I've already presented quickly with the figure how the two velocity components differ. So let's consider the velocity component along x. In this particular example, note that the symbol for velocity is v naught or v sub 0, which means that we consider the initial velocity of the projectile and relate it to its components. Since we are calculating the x component, we can imagine a right triangle to be drawn relating the initial velocity and the initial velocity components x and y. Since our concern for the meantime is the x component, we can focus our attention to v naught x here, which is the x component of the velocity, the initial velocity. And then in a while, we'll talk about the y component of the initial velocity. Notice that the initial velocity along x is related to the angle, and its relationship is the v naught x is adjacent to angle theta here. Since it's adjacent, the significant trigonometric function that we should be using is cosine ka. From our recall of trigonometric functions and recalling the mnemonic device SOHCAHTOA, since it's adjacent, that's ka, that's cosine of the angle theta is equal to adjacent over hypotenuse. Notice that the hypotenuse is represented by the initial velocity here, or v naught. And to calculate for v naught x, we have v naught cosine theta. Notice that in the initial presentation that I had in the previous figure that I've shown you, the initial velocity x, or v naught x, the component of velocity initial, is consistent throughout the path of the projectile. That is, whatever is v naught x that we'll be able to calculate, that would be the initial velocity, that would be the component of the velocity along x throughout the path of the projectile. Next, we compute the velocity component along y. We follow the same pattern, but this time we are concerned about the y component. Notice again that the y component of the velocity here is related to the angle theta here. And the relationship is that the angle theta is, the v naught y rather, is opposite that of the angle theta. Since it's opposite, we recall SOHCAHTOA and we'll be using sine, since the related mnemonic is SOH. So sine of the angle theta is equal to opposite over hypotenuse. And again, here, the opposite side is v naught y over the hypotenuse, which is v naught. And rearranging your equation, you get v naught y is equal to v naught sine theta. Our next concern is for us to know the details of the component, say the horizontal component of the acceleration and the vertical component of the acceleration. Notice in the figure that the velocity component along x does not change. And we define acceleration to be the change in velocity. So since there is no change in the velocity along the horizontal, we note that the acceleration of the projectile along the horizontal is 0. That means that the object does not speed up nor slow down nor change in direction when we talk about the horizontal component of motion. However, if we talk about the velocity component along the y, we notice that there is change in velocity. That change in the velocity of the object as shown by the arrows getting smaller as the projectile moves up, and the arrows getting larger as the projectile moves down. This means that the projectile is accelerating downward, and that downward acceleration results to a negative symbol or a negative sign. The value of the acceleration due to gravity on Earth is 9.81 meters per second squared. And once again, that's downward. When you go to other heavenly bodies such as the moon, the acceleration due to gravity changes. Say, with the moon, the acceleration due to gravity value is 1/6 that of the value on Earth. So that's around 10/6, or that's 5/3 downward. So once again, the horizontal component of the velocity is consistent. That leads us with the idea that the acceleration is 0 along the horizontal. And the velocity changes along the y such that as the object moves up, the velocity becomes lesser. And as the object moves down, the magnitude of the velocity increases. And that means that acceleration due to gravity is negative, or that's downward. Once again, the gravitational pull contributes to the vertical component. The gravitational pull depends on the mass of the objects in question. And relatively, the acceleration due to gravity is constant here on Earth. And it's also constant when you go to the moon or some other heavenly bodies, if ever that would be possible. We now recall our basic kinematic equations and see how our projectile motion equations change with it. When we discuss kinematic equations, we usually focus on the first three as definitions. Definition of displacement, which is the product of average velocity and time. Definition of average velocity, that's initial velocity plus final velocity divided by 2, or that's v1 plus v2 divided by 2. And the definition of acceleration is the change in velocity, or that is v2 minus v1 all over 2, all over t rather. We use these three equations for us to be able to derive three more equations. So the three more equations that we have here were actually derived from combinations of 2 or 3 of the kinematic equations that we have defined initially. So equation number 4 here is actually a combination of equations 1 and 2. Equation 5 is a combination of all three, as well as equation number 6. Now, if we are to change our equations here and contextualize it to that of projectile motion, we know that changes that we can consider. Say, if it's the vertical motion that we are to calculate, would get y is equal to vy, average vy, t. Or if it's x component that we are to consider, that's x equals vxt, which is more appropriate in our calculation. And then notice the most significant change that we consider with our kinematic equations would be with the acceleration symbol. The symbol for acceleration due to gravity is g. And since what's considered constant in our projectile motion topic is g, we replace our symbol for acceleration to be g, or with the value negative 9.81 meters per second squared, or negative 10 meters per second squared. There. So the velocity component along y at the maximum height is 0. This is another trivia that we should take note of. Although I've already mentioned it earlier, it's important for us to reiterate that it's the y component of the velocity that becomes 0 at the maximum height. And though the maximum height velocity component along y is 0, there still is motion. And that motion is associated with the horizontal motion of the projectile, which is constant in terms of velocity. Again, notice that this arrow here symbolizes that the projectile is still moving. Now, we can calculate an expression, or we can have an expression for the range as well as the maximum height for easy reference in calculations. Later, when you do calculations with projectile motion, you'd note that you will be needing basic concepts and equations associated so that you'll be able to easily solve problems related to projectile motion. We take note that if we are to calculate the range is independent of the vertical motion, so we can quickly consider those that would affect this particular quantity, which is the range. The range simply is dependent upon the constant velocity of the projectile and the time it takes for the projectile to move from one position to another position. So essentially, the equation is simply R is equal to V naught xt. R again is the range, which is the horizontal displacement, and V naught x is the initial velocity along x multiplied to that of the time it takes for the projectile to move from one position to another position. So that's the equation for the range. You can actually expand this equation knowing that we have already expressed V naught x to be V naught cosine theta times time. We can further expand time to have or to take another form, and we'll be talking about that in a while. So the time it takes for the projectile to cover this position to that point, the end point where the projectile will stop or ideally reach, if ever it won't stop, relates to two other values of time. We can consider the time it takes for the projectile to go up and another time, which is the time it takes for the projectile to go down. Some simple relationships from this figure tells us that the time it takes for the projectile to go up is equal to the time it takes for the projectile to go down. And the total time of flight of the projectile simply is twice any of those. That's twice the time in going up or twice the time in going down. Or that's t up plus t down. So we can now consider how we can express time. And in this case, we can consider the time in going up initially. Notice that for a projectile to go up, we can consider some of the basic quantities that we can consider. And those quantities include, number one, the initial velocity. Another one, the initial velocity here is v1. And then since the time in going up that we are to consider tells us that the y, there are a lot of quantities that we can consider along the y. And that explains why we will be more interested in considering y values rather than the x values. So we consider v1y or v naught y, or the velocity initial component along y, which is v naught y in this case, and that is v naught sine theta. And we consider the final velocity of the projectile when it reaches the maximum height, since we are to consider the time for the projectile to go here. The velocity component along y at the maximum height, once again, is 0. So if we are to consider our kinematic equations, particularly equation number 3, we note of this equation. You notice that the final velocity here is 0. That's why our expression for the acceleration equation becomes this. The final velocity once again becomes 0. And we can manipulate our equation such that we get acceleration due to gravity times the time in going up is equal to negative v naught y. And since we're calculating for t up, We divide both sides by g and get this expression. And then finally, we plug in what we have initially calculated, expressed for the initial velocity component along y, and we'll get negative v naught sine theta. And the final expression is this. The time in going up for a projectile is negative v naught sine theta all over g. Take note that the time in going up is positive. Time in going down is also positive. And all expressions of time should ideally be positive, because getting negative time would mean going back in time, or some other interpretations that we'd have as to some other signs of time. In order for us to be able to get positive time, note that this negative sign cancels with the negative value of the acceleration due to gravity. Again, g is negative 10 meters per second squared, or negative 9.81 meters per second squared. Now, to get the total time of flight, we simply double the time in going up. So the expression capital T equals this value simply tells us that for us to be able to calculate for the total time of flight, we simply double what we initially expressed for the time in going up. Once again, T up is equal to T down. Next, we can calculate the maximum height. And the maximum height, once again, is can be calculated by considering one of the expressions, one of the equations that we have for projectile motion. And that's equation number 6, this equation. Again, the equation that we have here considers final velocity along y at the maximum height to be 0. That's why this becomes cancelled and be equal to 0. So what becomes of our expression would be this. We now replace the symbol d, which is displacement, with what we are concerned about. That's height. So instead of writing d sub y, we can have h, which tells us this is maximum height. Different references would use different symbols or notation for expressing the quantities that they are expressing. And in this case, maximum height is h. And that's equal to negative v naught y, or that's the component of the initial velocity along y squared all over 2g. There. And again, we can express our v naught y to be equal to v naught sine theta, and that's what we have here. Notice that when you expand v naught sine theta and you square it, you actually get this expression. That's negative v naught squared. Look at where the exponent 2 gets in. That's sine squared theta, or that could be sine theta squared. But it's not the theta that you are squaring. It's the expression sine theta all over 2g. And that's the entire equation for calculating the maximum height. Now we go back to our maximum range equation, which we initially expressed as r is equal to v naught xt. We take note again that v naught x is v naught cosine theta, and we look for an expression for the time, the total time of flight of the projectile, and we plug it into our values initially. So that's what we have here. That's negative 2 v naught sine theta over g. That's capital T, or in this case, I represented it with lowercase t to symbolize the total time of flight. And the expression for v naught x is v naught cosine theta. We simply plug in those values, those expressions, or equations rather, substitute, and you'll get this expression. V naught cosine theta times negative 2 v naught sine theta over g. Now, to simplify our equation, we take note of the double angle formula and get the following expression. There, sine 2 theta is actually equal to 2 cosine theta sine theta. And that's why you'd get this final expression for the range. That is negative V naught squared sine 2 theta all over G. And finally, to summarize the major equations that we need for projectile motion, we get to express total time of flight, we have T equals 2 V naught sine theta all over G. Maximum height reached is H equals V naught squared sine squared theta all over 2G. And for horizontal range, R is equal to V naught squared sine 2 theta all over G. Take note of those equations, of these equations, because essentially these are what we consider when we examine conceptual questions such as what would be the angle at which you throw a projectile for you to be able to get the maximum height or the maximum range. Now, we can also consider effects of air resistance to make calculations more realistic. We disregard air resistance for ideal setups, but for us to approach reality, we need to factor in air resistance. Consider the following, this particular picture, and notice that because of air resistance, the actual path becomes different with that of the ideal path. So we take note that because of air resistance, the motion of projectiles become different. And in order for us to approach reality, we need to factor in effects of air resistance. Another picture to showcase effects of air resistance is this. This figure shows us the parabolic paths of a projectile that's thrown at with different conditions. And notice that a projectile that considers this green figure here, this green graph here, actually is able to travel a greater horizontal distance and a higher vertical displacement. Notice that the ideal path has a much larger x and y displacement. Same goes with other projectiles. That is, for a projectile that's represented by the path by the figure or the graph colored red and colored blue. So indeed, if we factor in air resistance, the distance or the displacement that will be covered by projectiles will be lesser, both for displacement along y and displacement along x, as illustrated by the two figures that I've shown, the previous one from the previous slide and this one here. Now, let us consciously consider some conceptual questions such as, at what angle should a projectile be fired to reach the maximum height? In order for us to answer maximum height question, we need to recall the equation from the summary. And this equation for maximum height tells us that there are several factors that could affect the maximum height value. And if it's the angle that we are to talk about, we need to note how we'd be able to get a maximum value 1 rather than getting a 0 value. So the question here is, what should be the value of the theta so that sine theta becomes maximum, or that is 1? What do you think? So if we consider sine 0 and calculate, let me show you, let me share another screen. and calculate the value of the angle at sine 0, we'll be able to get 0. So it will not be maximum if the angle is 0. And we try out sine 90. That is, if we throw a projectile at 90 degrees with respect to the horizontal, 90 degrees, what do you think will happen? Let's check. There. So for maximum height to be reached, the value of the angle at which you are to throw a projectile would be at 90 degrees with the horizontal. It simply makes sense. That is, if you want a projectile to reach the highest, you throw it upward. It makes sense. The second question that we are to consider would be, let me just quickly share my slide again. Is what now would be the value of the angle so that it will reach the maximum range. So since it is a range equation, we need to consider our range equation here. Since the question is about range, we need to consider the range equation. And the range equation tells us that the quantities or the factors that affect the range are as follows. Number one is the initial velocity value, and the second one is the angle. And take note, that's double angle. That is, we need to have a value of the angle multiplied by 2 such that it will be maximum. And maximum means 1. In answering the previous conceptual question that we had, we need to get 90 for us to reach a sine 90 value that's maximum. That's 1. That means that for us to be able to get 90 for this second conceptual question, we need to divide it by 2. So that's 45, such that 45 times 2 is 90, and sine 90 is equal to 1, as shown in our previous calculation. So that means that in order for a projectile to reach its maximum range, you need to throw the projectile at 45-degree angle. And once again, to answer the projectile, the conceptual questions related to projectile that we have, question number 1, at what angle should a projectile be fired to reach the maximum height? Again, with respect to the horizontal, you should throw it at 90 degrees. 90 degrees with respect to the horizontal. And at what range, at what angle rather, should a projectile be fired to reach the maximum height? Again, that's at 45 degrees. 45 degrees. Now, an activity that we can do for us to explore further projectile motion are as follows. One of those activities that we can do is to create a projectile launcher. And in order for us to be able to create a projectile launcher, we need to consider some objectives that relate to why we are discussing projectile motion. First, the competency that's related to projectile motion can be found in grade 9, that's science 9, in grade 9 physics topic. That's the code is S9FE-1V, or that's 4th quarter A, first week. Competency number 34. Describe the horizontal and vertical motions of a projectile. I've analyze the free flight motion of a projectile motion. And another competency that can be found in the DepEd K-12 curriculum is investigate the relationship between the angle of release and the height and range of the projectile. The code is also reflected. So in doing the activity, we can consider the following materials: 10 pieces rubber band, 1 protractor, 1 ruler, 1 plastic cup or spoon, 15 pieces popsicle sticks, tape, and 1 marble. This activity can be done in groups such that all groups would be given the same materials only, same materials, so that if they do the activity, they can compare. And for the procedures, number one, you can form small groups with a maximum number of 5 members. And then each group must have a partner group to compare. And number two is each group will be tasked to prepare a fortress or a projectile for later that can be hit by the projectile, given 3 short bond papers. Each group will be tasked to design a projectile launcher that will be able to meet the following objectives: be able to launch at the highest and farthest possible position, be able to hit a built fortress. And number four, each group will be tasked to prepare the projectile launcher based on their prepared design, given all the materials provided. Here are some illustrations to showcase how one could build the projectile launcher. There. And item 5, each group will test the horizontal and vertical distances covered by their launcher. Each group will take turns hitting an opponent group's fortress. And item 7, consider releasing the projectile at different angles. And each release, there should be 3 trials for the students to be able to consider the factors or identify factors that could affect the distance covered by the projectile. For the data, you can consider the following table. Say at 30 degrees, what would be the value of the range and the height covered by the projectile? Usually you can focus on the range initially. 45 degrees and 60 degrees. You can add some other angles such as 90 degrees or angles in between. And that's it. You can also answer the following analysis questions as part of the activity. What caused the success or the failure of your projectile launcher? What factor did you consider in your activity? How does it relate to the distance covered by the projectile? How do you relate the angle of release to that of the horizontal and vertical displacement of the projectile? And number 4, what factors affected the distance covered by the projectile other than the angle of release? Other than doing this activity, you can also consider online simulations. You can quickly check online and a projectile launcher simulator. You can find the projectile motion fet here, and you can run the simulation. And in this simulation, you'd be able to see the path, the ideal paths of projectiles when launched at different conditions. The simulation in a while will showcase or will show you the different conditions that you can consider. Say here is a laboratory activity there. Some of the factors that you can consider in this particular simulation are as follows. There. So you can have this as you can change the object or the projectile that you can throw, say a pumpkin, or initially that's a cannonball. And then the mass can be varied. You can move this tab here. You can set it at default for a certain value, say any value, 16.6 kilograms. And then you can also change the diameter of the object. You can also change the gravity, but initially it's set at default at 9.81 meters per second squared. You can also add air resistance and consider what happens if there is air resistance. And in this simulation, your challenge is to hit that bullseye. And let's see. You can change, by the way, another one is change the angle and the initial speed of the projectile. Let's check it out here. And you can press this icon here to release the projectile. Ta-da! Oops, I was not able to hit it. I'll increase the angle and check it out again. Oh, yay! Almost. Decrease it a little and release it again for the third time and check if it hits. Yaps! Almost. And you can include air resistance and see what happens. There. It becomes lesser. Because of air resistance, I was able to hit the bullseye. You can again consider others, other projectile here, projectiles, and see, oops, there, tank shell, or let's consider a piano. There. Whoa. There. Or change some other variables that you can see in this presentation. Now going back to my slides, and this is almost over. The last portion of my presentation is a post-its. Initially, I asked you 10 questions, and this time I'll be revealing the answers to the questions. For the first question, when a teacher throws an eraser from the front to a door 6 meters away, how do you call the parabolic path taken by the eraser? The answer is trajectory. Number 2, when a ball is thrown by a physical education teacher, the ball follows a parabolic path. What do you call, or how do you call the ball in this case? The answer is projectile. Item 3, a ball thrown at a certain angle is aimed to travel the farthest. So that is maximum range. At what angle with respect to the horizontal will accomplish this? The answer is 45 degrees. Item number 4, maximum height. The answer is 90 degrees. Item 5, which of the following statements about projectile motion is not true if air resistance is neglected? Letter A, the graph of V versus time for horizontal and vertical are the same. They're actually different. Number 6, two vehicles fell off a cliff and follow the paths X and Y as shown in the figure below. Which statement below is true about the situation? Number 1, they covered the same horizontal displacement. This is wrong. This is obviously wrong because Y covered a greater displacement. Number 2, they have the same vertical acceleration throughout. That's true. The acceleration of the two objects is equal to the acceleration due to gravity. So 2 is our choice. Meantime, number 3, their velocity components along the horizontal are the same. That's once again, their velocity components along the horizontal are the same. That's not true because Y was able to cover a greater distance for the same amount of time. That means Y has greater horizontal velocity. So number 3 is also not true. That means that we're left with 2 as our option, and the best answer is letter B. Item 7, a ball is thrown from a cliff and follows a path similar to the figure below, neglecting air resistance. Which of the following statements about the falling ball is correct? Okay, first one, the vertical acceleration of the ball increases. That's wrong because the vertical acceleration is constant, and that's equal to the acceleration due to gravity. Number 2, the vertical component of the velocity of the ball increases. Vertical component of the velocity of the ball increases. That's true because as the ball go down, it accelerates. That means its vertical component of the velocity increases. So far it's 2 again. The horizontal component of the velocity of the ball increases. This is not true. Again, the horizontal component of the velocity is constant. So the answer here is 2 again, and that's letter B. Item 8, a soccer ball is kicked by a player during a match. Which pair of velocity time graphs represent the horizontal and vertical components of the ball as it reaches the maximum height? As it reaches the maximum height, the horizontal velocity of the projectile is constant. So A is correct. Letter B is wrong. C is correct. Letter D is wrong. So it's between A and C. Now let's consider the vertical component. as the projectile, that is in this case the soccer ball, go up, its velocity component decreases until it becomes zero at the maximum height. So the best answer here is letter C. There. Item number 9. After hitting a baseball, the horizontal speed was measured to be 30 meters per second forward, and its vertical speed was 35 meters per second upward. Ignoring air resistance, what is the value of the velocity 2 seconds after? Acceleration due to gravity is 10 meters per second per second. Again, first, we consider the horizontal motion. The horizontal velocity is not changing. So 30 meters per second forward will be maintained. So you should be able to see 30 meters per second there. So it's between A and B. And then if it's 2 seconds after, that's 2 times 10, that's 20 meters per second squared. And let's recall what the question is asking. After hitting a baseball, the horizontal speed was measured to be 30 meters per second forward, and its vertical speed was 35 meters per second upward. So if it's going up, ideally it will be moving, it will be pulled downward. So its velocity will decrease by 2 times 10, by 20. So that's 35 minus 20 is 15. So the best answer is letter B, 30 meters per second horizontally and 15 meters per second upward. And then finally, number 10 is a tennis ball was hit, giving it a vertical speed of 10 meters per second upward and a horizontal speed of 25 meters per second. How far will it be able to travel horizontally? This is a bit tricky, but the idea here is we need to take note of the value of the vertical speed, which is 10 meters per second. So it will take 1 second for it to be able to reach the maximum height. And then 10 meters per second downward again, that's 2 seconds. Total time of flight is 2 seconds. And 2 seconds times the horizontal speed, 25 meters per second, is 50 meters. And the answer is letter D, though. And that's it. That's the end of my presentation. I hope you understood something about projectile motion. Till my next episode. Salamat.